Imagine you have a graph where the nodes are linked by edges, and each edge has a weight representing its cost, distance, or importance. Dijkstra's algorithm helps determine the shortest path from a starting node to all other nodes in a network. Imagine these nodes representing airports and the edges representing flight routes. The algorithm can calculate the minimum travel distance or time from one airport to every other airport in the network. Let's examine this graph more closely and find the shortest distance from node A to all the other nodes. Dijkstra's algorithm makes this simple. All we need to do is keep track of specific details as we go through each step of the process. The first thing to track is which nodes haven't been visited yet. In the initial step, we mark all nodes as unvisited. To do these, we set up two lists. One list will contain all the unvisited nodes in the graph, starting with every node included. The other will be a visited nodes list, which begins empty. Next, we assign a tentative distance value to each node, which will update as the algorithm progresses. We can use the table on the right, which has 3 columns. The first column lists the nodes. The second column shows the current shortest distance from node A to each node. At the start of the algorithm, we only know the distance from A to itself, which is 0, while the distances to all other nodes are set to infinity since they are unknown. The third column keeps track of the previous node on the shortest path to each node. Initially, this column is empty because we don't have any path information yet. These are the key details we need to track. Now let's begin the first iteration. Starting at node A, we calculate the distances to all its unvisited neighbors. The distance from A to B is 2, and the distance from A to D is 8. Now we update our table on the right. Next, we update the table. If we discover a shorter distance to any unvisited node, we update their values. Currently, both B and D are unvisited, and their initial distances are set to infinity. We update the distance from A to B to 2 and record A as the previous node in the table. The same process applies to node D. We update its shortest distance to 8 and set A as its previous node. With that, this iteration is complete. We mark A as visited, move it from the unvisited nodes list to the visited nodes list. The final step is to select a new node as the current node to continue exploring the graph. To continue, we always select the unvisited node with the smallest current distance. Based on our table, node A has a distance of 0 but has already been visited, while node B is unvisited with a distance of 2 and node D is unvisited with a distance of 8. All other nodes still have a distance of infinity. Since B has the shortest distance among the unvisited nodes, it becomes the current node. From here, we return to step 3 and calculate the distances to all unvisited neighbors of node B. The unvisited neighbors of B are E and D, and the distance calculations are as follows. Since B has a current distance of 2, we add this to the weight of the edges to its neighbors, E and D. Let's first consider node E. The distance to E through B is 2 plus weight of the edge from B to E, which is equal to 8. Now we compare this new distance 8 with the current shortest distance for E stored in the table, which is infinity. Since 8 is indeed less than infinity, we update the shortest distance for E to 8 in the table. We update the shortest distance to node E and mark node B as the previous one. Now let's move on to node D. The new distance for D is 7, which is 2 plus 5 from A through B. We need to compare this new distance of 7 with the current value of 8 in the table, and since 7 is smaller than 8, we update the shortest distance to 7 and set node B as the previous node. Now that we've checked all unvisited neighbors of B, we can mark B as visited node and move on. In the next step, we select a new current node from all the unvisited nodes, picking the one with the smallest distance. In this case, node D is the one with the minimum distance of 7. Next, we calculate the distance to all unvisited neighbors of node D. Since the shortest distance from A to D is currently 7, we add 7 to the distances of its neighbors. First, let's consider node E. The distance from A to E through D is 10, which, since 10 is not smaller than the current distance of 8 in our table, we don't update the distance to E. Now, for node F, the current distance in our table is infinity, but through D we get a distance of 9, that is 7 plus 2. So we update the shortest distance for F to 9. We update the distance to node F to 9 and set the previous node to D. Now we can mark D as visited and move on to the next unvisited node with the smallest distance. The next node with the smallest distance is E, as it has a distance of 8, while F has a distance of 9 and C has an infinity distance. Now we calculate the distances from E to C and from E to F. Since the current distance from A to E is 8, we add 8 to these distances. Starting with node C, the distance from A to C through E is 17, which is 8 plus 9, which is less than infinity. So we update the distance to C to 17. We update the table by setting the shortest distance of C to 17 and the previous node to E. When we check node F, we see that the new distance is 9, which is the same as the current distance in the table, so we don't make any changes. Now we are finished with node E. Now we have F and C left as unvisited nodes. Since F has a distance of 9 and C has a distance of 17, we always start with the node that has the minimal distance. So we begin with F. The only unvisited neighbor of F is C. If we go through node F, we get a distance of 12 from A to C, which 9 plus 3. Since 12 is less than the current distance of 17, we update the distance to C. Therefore, we update the shortest distance to C to 12 and set the previous node as F. After marking F as visited, we are left with node C. Since C has no unvisited neighbors, we mark C as finished. At this point, we have completed the algorithm and the table is also complete. We now have important information about the graph. We've calculated the shortest distance from A to every other node, and we also have the previous nodes, which will allow us to reconstruct the shortest path from A to any node by tracing back from the destination node to the start. For instance, if we want to reconstruct the path from A to C, we first see that the shortest distance is 12. To find the shortest path, we start at node C and look at its previous node, which is F in the table. From F, we can continue tracing back to the previous node, and so on, until we reach the starting node A. Starting from F, we mark the path from F to C. Now, we look at F and see that its previous node is D. We continue tracing the path backward from D. We mark the edge from D to F. Now we look at node D in the table and see that its previous node is B. We continue tracing the path backward from B, we mark the edge from B to D. Then we look at node B in the table and see that its previous node is A. Finally, we mark the edge from A to B, completing the reconstruction of the shortest path from A to C. The path is A, B, D, F, C. Now we have found the shortest path from A to C, which has a length of 12. The path is A, B, D, F, C, and this is the shortest connection between A and C. I hope this video made Dijkstra algorithm clearer for you. If it was helpful, don't forget to like and subscribe for more computer science and trading content. Thanks for watching, Dr. et al.